Okay, so today we're in section 4.1, factors and prime factorization. This is actually the exact same section and chapter and lesson in your 7th grade book. It's just, so 2/3 of the lesson are going to be kind of review from the 7th grade curriculum, and then we're going to add into that just the algebraic part of it. All right, so you can abbreviate these definitions, but you need to know the difference between a prime and a composite number. A prime number has no other factors besides 1 and itself. So you don't have to write that whole first part of it. You can just say no other factors besides 1 and itself. That's a prime number. A composite number has more than just those two factors. So it has another factor besides 1 and itself. Composite numbers have another factor, at least one other factor, other than 1 and the number itself. A factor, this is kind of a technical definition, but a factor is basically a number that can be evenly divided into another number. For example, we take the number 10. Factors of 10 that can be evenly divided into 10 are, we think, 1. What's another number that can be evenly divided into 10? 2, 5, and 10. These are what we call factors. These factors can be evenly divided into 10, so they meet the criteria. All right, the last thing is you need to understand that the number 1 is not prime or composite. It's neither. So that looks to me like a really good true-false statement or even a short answer question. You need to know that the number 1 is neither prime nor composite. Example 1 is a yearbook example. It says your school yearbook will have 24 photos in a rectangular display. So think rectangular display, 24 photos. If you want no more than 10 photos in a row or column, how many ways can you arrange them? And obviously this is, so there's an even number in each row, all right? So, and no leftovers. So we need to figure out, all right, what are the factors of 24 that would meet this criteria? Well, we start off with the number 1, 1 times 24. Does that meet the criteria, no more than 10 photos in a row? No, if you just line them up straight across, 24 photos, no, that doesn't meet the criteria. All right, what about 2 and 12? Does that meet the criteria? No, it doesn't. 12 is still more than 10. So 2 rows of 12 is still more than 10 photos in a row, so that doesn't work. All right, so these two don't work. What about 3 rows of 8? Okay, that one's good. What about 4 rows of 6?
Yes.
Yep, that one's good. What about 6 rows of 4?
Yes.
Yep. And 8 rows of 3?
Yes.
Okay. And now that we're looking at some of these repeating factors, we know that we've covered all of the potential combinations that can be multiplied together to equal 24. So I see clearly that there are 4 possible ways to display this. All right. In your notes, I want you to write numbers 46 and 56. 2 homework problems tonight that are very similar to this example. All right, where you have to figure out what combinations would give you that total, and then which one of those combinations would meet the criteria. Now, let's take a number, and we're going to write all of the factors of that number. So, factors mean that this number goes evenly into that number. All right, but instead of just randomly writing down numbers, okay, yeah, I know, like 3 times 10 equals 30, so those are 2 factors. You want to go in some type of numerical order so you don't miss anything. The way you do that is you start with the number 1. Well, there's always going to be a factor of 1, right? 1 times whatever that number is. Start with 1. Then work your way up to 2. Is 2 a factor of 30?
Yes.
Yeah, 2 times what? 15. We just said 3 times 10. What about 4? Is 4 a factor? No, it doesn't go evenly. What about 5?
Yes.
Yes, 5 times 6. Very good. And then what about 6? 6 times 5. But do you see, guys, 6 times 5 is the same thing as 5.5 times 6? Y'all see that? So I know that I'm done listing my factors. As soon as they start repeating, I know that I'm done listing my factors. And now I can work my way down the first row and then back up the second row to make sure that I list all of my factors. So I go down the first row, 1, 2, 3, 5, and then I go up my second row, 6, 10, 15, and 30. And notice, guys, that your first and last factors that you list should be 1 in the number itself, okay? And then everything in between, you know, those are other factors as well, all right? And that would be what we call listing all of the factors of 30. So let me ask you this, going off of our definitions, is this number prime or composite? Why is it composite?
Because there's multiple numbers that can.
Because there's more factors than just 1 in the number itself. So I call it a composite number. All right. I want you to do 31. List all the factors of 31 and then tell me, is that number prime or composite? So is 31 prime or composite? It's prime. All right, 87, 1 and 87, and 3 and 29. So this one is also composite. All right, I want to teach you real quick a little hint to figure out that 87 is divisible by 3. Does anybody know the shortcut to figure out if 87 is divisible by 3, Janie?
You add the two numbers together, and if it's a
Multiple,
6 or
yeah,
multiple.
yeah. Very good. So what's 8 plus 7?
8 plus 7 is 4.
It's 15. So 8 plus 7 is 15, and yeah, 15 is a multiple of 3. So I know that 87 is also divisible by 3. All right, so I can add the digits together. If that comes to a number that I can divide evenly by 3, then I know 3 is a factor. All right, so prime and composite numbers. Okay, example 2. In example 2, we are going to learn something called prime factorization. Okay, with prime factorization, you are writing the number as a product of its prime numbers. Okay, so prime is a very important word here. So in example 1, we found the factors, all of the factors. Well, some of those factors were composite numbers. Okay, that's fine. But when we do the prime factorization, we're breaking a number down into its prime factors or components. All right, so we think of something that requires assembly. What's something that requires assembly? A car, Legos. Okay, Legos was an example used in another class. All right, something that requires assembly. So when we put it together, it's one unit when we put it together, right? But can we take it back apart if we wanted to? We could take it back apart and break it down into all of its pieces. That's what we're doing when we're factoring something. Okay, when we're factoring a big number, we're not changing its value. We're just revealing its prime factors that make up what that number is going to be. All right, so let's take 630 for example. 630, if I were to do the prime factorization, we are not going to use factor trees in this class. We're going to use a method called upside down division. And it's exactly what it sounds like. You write the number and then you write an upside down division symbol underneath that number, just like you see on the screen. So go ahead and do that. All right, and here is the number one most important thing with upside down division. You must divide by a prime number. Okay, so while 630 is divisible by 10, 10 is not a prime number. So I can't do upside down division with that number. What is a prime number that would be divisible by 630? 2, 3, because 6 plus 3 is 9. 5. Okay, it doesn't matter what number you start with as long as it's prime. All right, so I'm going to start with 2. Okay, if it's an even number, I know 2 is going to be a factor. All right, 2 goes into 630 315 times. All right, well, 2's done because 315 is odd. What's a prime number that could go into 315? 3 or 5, either one. Okay, 3 goes into 315 105 times. All right, now maybe 3 again. Okay, and that's going to be 35. And then 5. And then 7. And as soon as your bottom number is prime, so 35 wasn't prime, so I kept going, but 7 is prime. As soon as your bottom number is prime, you know you've completed the prime factorization. Now you need to double check something. Are all the numbers on the outside of the division, are they all prime? If your answer to that is no, maybe you forgot and you divided by a 10. Or you divided by a 4 and you forgot, then this is where you'll see that and you can go back and make the changes. Your prime factorization can only have prime factors. That's why it's called what it is. Now, when I'm listing my prime factorization, I'm going to write my repeated prime factors as powers. So because 3 repeats itself, I'm going to write it as an exponent. 2 times 3 squared times 5 times 7. And this is the prime factorization of 630. But here's what I want you to understand. We haven't changed the value of 630. I want you to put this in your calculators. Just put the whole thing in your calculator. 2 times 3 squared times 5 times 7. All right, what did you get when you multiplied those numbers together? 630. So you see, guys, we didn't change the value. All we did was we took a big number and we broke it down into its prime factors. That's all we did there. All right, and we're going to learn in 4.2 how to use those prime factors to actually find the greatest common factor between two numbers. All right, so prime factorization is important. I want you to do this next one, 550. I want you to do this one on your own. Do the prime factorization. Remember, if there's repeated prime factors, I want you to write them as exponents. All right, so prime factorization of 550. What did you start by dividing? 5. You did 5? Okay, I did 5 too. All right, and then 110, 5 again, 22, 2, and 11. All right, so when you write this prime factorization, you need to make sure that you write it in numerical order. So which prime factor is the smallest? 2. 2 times 5 squared times 11. All right, and that's the prime factorization. Who got that right? Okay, prime factorization, very good. So that's how we're going to do that. Now, in example 3, we're going to learn how to factor monomials. All right, so this is our algebraic application here. A monomial is a number, so 10, 20, 30, okay, that's a monomial. It's a variable, so m, x squared, y to the third, those are monomials. Or it's the product of a number and a variable raised to powers. And notice it said product. It didn't say sum, it didn't say difference, didn't even say quotient. So a monomial can also be numbers being multiplied by variables like we see right here in the chart. But notice very specifically, it is not addition or subtraction, what we see to be not monomials. Okay? So it's very important that we understand the difference. So if I have a monomial, I can factor it in much the same way that I've just factored numbers by themselves. Okay? And let's look at how we would do that. All right, so to factor the monomial, 28xy to the third power. All right, well, the first thing I want you to do is to do the prime factorization of 28. All right, upside down division, go ahead and do the prime factorization of 28. All right, so we have 2, 14, 2, and 7. So 2, 2, 7. Do y'all agree? So here's what our book says to do. When we're only doing prime factorization of numbers, we can write repeated factors as powers, no problem. But when it's a monomial, we need to write everything in expanded form. So what that means is it's going to show 2 times 2 times 7. Now I need to look at the variables and their powers. Okay, I know that if a variable is raised to a power, it's that variable multiplied by itself that many times. So I'm going to write it in expanded form. How many x's are in that term? No, x's. 1. How many y's are in that term? So times 3, or I say times 3, times y, times y, times y. And that is the factorization, the prime factorization of 28xy to the third. I just write it all in expanded form. So we factored 18, 2, 3, and 3. Did y'all get that? 2 times 3 times 3. All right, say the rest with me. Times s, times p, times p, times p, times p. Awesome. Why did I do 4 p's?
Because it's 4 times.
P to the 4th. Yeah, very good, because it's p to the 4th. So now I've factored that monomial. All right, and if you understand that, that's everything you need to know for 4.1.